Good morning, and thank you very much for having me here. Today I will talk about our efforts for the last 3-4 years at the University of Manchester in creating an ecosystem that enables to do research on virtual machines on low-power Arm-based devices. I will start by motivating a little bit why we believe having visualization at the IoT level it's a good thing to have. What are the opportunities and the challenges? And then I will talk about Maxine VM on Arm and our progress so far and our vision regarding the ecosystem. So if we, I'm sure you have seen these slides before. On one hand, we have big data that are processing data streams, and on the other hand, we have IoT devices that they enables for data. So essentially, what happens is either directly or indirectly, the IoT devices, they stream data on a framework, for a data platform, and then we actually consume the data and do analytics. And somebody can say, or somebody can view this model as a producer-consumer model in which the sensors or the devices, they send data for big data. But ideally, we would like to view the system as a big system that it works in collaboration in order to achieve the target, which is the analytic side. And we would like to achieve higher performance, of course, and throughput and latency, and somehow to be able to understand and convey information from the big data side to the sensors regarding how to throttle the data in order for the platform to catch up processing. If we see a typical deployment, which, I mean, from my perspective, this data can come from smart devices, sensors, or even social media, and in the platform for processing, either directly, they can stream directly on the platform, or through a gateway or a honeypot. If we take a step back and actually we see the architecture and the programmability of these different devices, we'll see that typically big data platforms like Spark, Flink, Hadoop, they follow the scale-out, scale-up approach, and they run on cloud or clusters on x86 typically. And these ecosystems are all, the majority of them at least, they are based on JVMs. So they have Spark and Flink and Hadoop. They are actually Apache projects that they run on JVM. And one of the key reasons of success of these platforms and why they became so popular, it's because since they're based on the JVM, they have rich libraries and ecosystems. So developers can write the applications either in Java or Scala really, really fast. And these ecosystems, every day, they're evolving. New are coming out, and new programming models, they are built on top of them. So these stacks, they're stacking up. They have platforms, and underneath we have resource managers, and they are becoming thicker and thicker when it comes to how much code they have to execute. On the other hand, if we take the IoT a smartphone, let's group them together for the discussion. Typically, or the majority of the times, they run on Arm devices, and they scale from milliwatts to watts. And of course, because they're low power, they are resource constrained. And if we see how these are developed, or we code them, we just use C or C++ or even Java or MicroPython, and there is a fragmentation in the programming models. So every vendor can support a different kind of OS that runs on a device or different programming model. And the challenge is, because we have this diversity and fragmentation of the programming models between the IoT side and the big data, they create in my opinion, 4 major drawbacks when it comes to the joining of these two worlds. The first one is the code duplication and maintenance. Imagine, for example, that let's take Apache Spark, for example, and we have a sorting operator. This sorting operator, theoretically, we could deploy a small one at least on the device, on the edge, and do there the sorting. But because this operator, which already exists on the big data side, we have to recode it and reprogram it for the IoT device that we have to do. That means that we have the same operator code in 2 different or 3 different languages, and we have to maintain them. And because we have so many different operators, we also have security and code validation issues. just compare this model, this fragmented model versus Android and Android Protect and Google Protect, and how all the Android applications, they are having a centralized point of verification. The third one is the lack of dynamic control. That means that the big data platform has a problem in communicating commands, let's say, to the edge to perform some operations like swap operator or stop streaming data or post data or drop data. And of course, the last one is the inability to perform decisions when it comes to performance and energy. So we cannot actually find some sensors that are the battery is drained and then trying to transition them in a low power state without actually switching them off. And if we go to application virtualization, so let's assume we decide to run a JVM on an IoT device. There are many solutions in the market regarding embedded JVMs, like the Jamaica VM, MicroEJ, even IBM J9 can scale down to a really small memory footprint. Because they are JVMs, they adhere to the right ones run everywhere approach. That means that theoretically, if we have the bytecode of one operator, we can just deploy it on the sensor and execute an existing operator on the edge. And following the similar trends like Android, for example, we could create a marketplace of operators. So everybody could upload their operator in this marketplace, like a sorting function or even a lightweight machine learning model, and then we can provide security and verification on a unified, centralized point of code maintenance. And since, in this case, both the big data platform and the devices, they're going to run the same code, or at least the same programming model, ideally or theoretically, we could just drag and drop operators from the big data framework to the devices, and therefore have dynamic data control over the data. But this is not very easy to do, because JVMs themselves, they have many complexities. They have a lot of baggage that come with JVMs since they were designed not for embedded execution, but for desktop execution, or now for clusters and big data. These overheads are Z compilation, garbage collection overheads, space memory constraints. Of course, there is some effort to provide specification for real-time JVMs, but in some cases, this can constrain the programming model. So the code you write in one JVM means something different in the other JVM. And of course, because they are complex systems that encompass many different compilers and subsystems, they are very power hungry. In order to find this trade-off, this sweet spot, how much of a JVM we really want to enable virtualization on IoT, ideally, we would like to have a virtual machine that is designed for research. So in the non-IoT world, there have been, through the last 15 years, a couple of research-based virtual machines that have really helped the community to find some solutions and some do research regarding performance mainly for desktop virtual machines. So we would like to create a state-of-the-art virtual machine for Java, for Arm architecture, both 32 and 64-bit, and be very fast and be very easy to change, so we can actually do very fast prototyping and experimentation. Be very close to reality, right? Because we don't want, let's say, a virtual machine for research that is far away from reality regarding performance, and enable us to do platform-specific optimizations. So for the last 3 years, in University of Manchester, we put significant effort to create such a platform. So have been building the Maxine VM, and the Maxine VM actually, it was a project that started at Sana Labs when I was intern back 2008, and since the version 2, the University of Manchester got the leading position in developing it. So the strength of Maxine VM is the following. It has a very modular design. That means every subcomponent of the virtual machine is a plug and play. So we can change everything during build time, starting from compilers, where we have 3 compilers, templates and optimizing compilers. We have schemes for object layouts and locking and how to reference objects. We have a set of garbage collections, so we can actually play between low power and non-low power garbage collections. And of course, we have a small C layer that provides the native threading and some runtime operations. So the last 3 years, we added support for Arm-v7 and AArch64, and we scaled the Maxine VM from 32-bit to 64-bit. And it has a comparative performance with industrial VMs, and it's fully open source, so everybody can actually check it out from GitHub and use it. And this engineering effort we have been doing for the last 3-4 years, mainly because Maxine VM, when it was first released, it was hard-coded for 64-bit only, and it was supporting only x86. We had to port and validate all the compilers to the ARM ISA, both v7 and v8. And because Maxine VM has 2 compilers, actually has 3, but we are mainly focused on 2, we had to do 4 ports of compilers into different architectures. And through our efforts, as you see in this graph, where we have the spec JVM and a couple of benchmarks, which are let's say the most famous benchmarks for JVM research, we have over 90% pass rate on spec JVM, and we have 60 and 77% on Arm-v7 and AArch64. And as today, I mean, we currently keep working on increasing the pass rate so we can match it with the x86 one, and we're also trying to do implement optimizations in order to match or at least come closer to the performance of the fastest JVMs in the market that are mainly from Oracle. But Maxine VM is not the only platform we develop. Maxine VM is just the core part of a larger vision that we have in our lab. So as you see in this picture, with the light blue color, we have some components that, in parallel with boosting the performance of Maxine VM on ARM devices, we also trying to port to Maxine VM. So Truffle, Graal, and MMTK are at the moment the state-of-the-art components for adding polyglot support in a virtual machine, so to make Maxine VM able to execute not only Java, but JavaScript, R, Ruby, and LLVM bytecodes. And also, we are actually porting the most advanced memory management toolkit from JaxRVM to Maxine VM. And essentially, when this vision is implemented and finalized, we will have a virtual machine that it can execute not any, but all the programming languages that are supported by Truffle, which is an Oracle product, and have really high performance because it will be based on the Graal compiler, which is the next generation compiler from Oracle in ZK 10, and be able to execute not only Java but multiple programming languages. And then all this platform will be running on Arm-v7 and AArch64. So ideally, practically, we will have one platform, fully open source, and then we will be able to optimize each programming language for each specific ARM architecture. So I'll try to motivate a little bit about why JVMs on IoT devices might be a good choice. Personally, I believe the biggest strength of this approach is the fact that we will be able, in this case, to create an ecosystem under one unified programming framework, and therefore this fragmentation of the programming models will at least not stop, but at least it will be less. And in this goal, we have been implementing research VMs on ARM devices. At the moment, Maxine VM is the state-of-the-art regarding research virtual machines on ARM devices. Here's the link to download it, and of course, we have an active team doing continuous development and improvements. And Maxine VM, we can check out our vision paper, the Beehive vision paper that describes how Maxine VM fits in the whole vision that we have for full stack hardware software co-design. So here I have a couple of slides for resources. You can check out documentation, papers, and the system. Our research has been funded by EBCRC grants, N-Scale Pamela Dome, and the European Union Horizon 2020 ActiCloud grant, and various Arm-i-case fundings. This is the name of our contributors, and we keep expanding the team. And I would like to thank you very much, and if you have any questions.
Okay, do we have any questions?
You talk about architectures you support from ARM. You mentioned V7 and AArch64. Have you considered even more constrained devices like M-class?
Yes, yes, we have considered this kind of devices, but the challenge is that at some stage we would like to run those devices. It just we haven't managed to scale Maxine VM to that level yet to be able to fit in the memory, because Maxine VM, I haven't mentioned it, is a metacircular virtual machine. So it is written in Java. It's written in the language it runs. That means that we have to create a boot image, which is a binary of Maxine, which at the moment it's 60 megabytes. So we have to make it even smaller. So at the moment, the smaller device we run is actually like smartphone level. But we have ideas how to make it even smaller.
Okay, thank you.
Hi, Jan Rellermeijer, TU Delft. I see many similar efforts in this area where people try to expand the scope of Java virtual machines beyond the Java language, right?
Yeah.
You're possibly aware that J9 essentially got open sourced.
Yes.
And I hear a lot of the same argument from their teams, right?
Yes, yeah.
At the same time, there were other metacircular JVM implementations that like Jike's RVM,
Yes,
right?
yes.
So where do you think is the distinct advantage of going this route, given that you have to put a lot of effort into getting close to the performance and the coverage that OpenJDK provides out of the box?
I will split my answer in two fronts. The first one is the comparative evaluation against other metacircular JVMs, so Jikes. So Maxine VM, the strength of Maxine VM versus Jikes is the fact that Maxine VM can support Graal, because Graal is the latest optimizing compiler from Oracle. That means that Maxine VM essentially will be downstreaming any optimizations that Oracle does to our virtual machine. And also Maxine VM is compatible with the JDK classes, while Jikes has the GNU class path, which is behind the development regarding the JDK classes of Oracle. Regarding IBM J9, which we talked with the team in Toronto, the benefit of Maxine doesn't try to compete with industrial quality or industrial strength virtual machines. It tries to create a platform that is comparative in functionality and performance, but it's much faster to experiment. So if, for example, in Maxine, you want to change your object layout, let's say, it's just one class you have to touch. Of course, in the expense of indirection and lower performance compared to like C++ or manual tune at JVM. So our objective is not to try to compete head-to-head with performance, but to be close enough and to have this experimentation and easiness to the developers and to the researchers to actually do research.
Okay, thank you. Let's thank our speaker.